Perfect. All right, pull my screen up. We'll start back here. If you guys want to follow along the study guide workbook as we go along here, that would be great. And again, I encourage you to ask questions if you can, or if you'd like to. Also, you can type stuff out if you're really not that comfortable talking. That's fine. I'm okay with that. This is meant to be a two-way conversation, though. So if you do have questions, please ask them. So we're going to start with 3 alpha. That's identifying the relationships, basic facts, and state general principles about the functions of the high frequency or HF transceiver modules. That's the radio y'all worked on yesterday. Does anybody know the nomenclature for the radio? Does anybody know the nomenclature for the radio? I'll give you a hint. It's the title of your TO. What did you say? Repeat yourself. Yeah, the AMPRC 150 Charlie. Yeah, that's correct. So that's actually the configuration of the radio when you have it in portable. It's actually called the RT1694 Delta. So that's the actual name for the radio, is the RT1694 Delta. And you can see that in your first TO on page 11, as well as in your guys' study workbook. When you look through the study guide workbook, it talks about some configurations, things like that you all were reading about for the radio. And one of the configurations says some equipment that may come with the radio, and the RT1694 Delta is on there, and that's the radio itself. All right. So moving on here, you guys saw on the bottom here, minimum 73% on your block test. That means you have to get 12 out of the 15 questions right to pass. There are many different HF radios in your career field. Each may be slightly different, but the basics are all the same. Understanding the following theory and block diagrams will give you a better understanding of how these HF radios function. And this is true for all radios we work on. So we'll skip ahead a little bit here to look at the diagrams. So if you can kind of understand how all of this stuff flows and works, it helps you become a better maintainer and a better person when it comes to troubleshooting radios as well, because you can break it down. And even though we do a lot of swaptronics now for our equipment and for our radios, you can actually help the manufacturer better by understanding how this stuff works and understanding when an error code pops up in your TO. You can go in there and look and say, oh, this is the error code that popped up. And when you send that back to the manufacturer, you're a lot more likely to get that radio back quickly, as opposed to getting it back at a much slower pace from the manufacturer than if you had sent them nothing or done no troubleshooting on your own. So we preach TOs a lot in this schoolhouse, and there's a reason for that. You have to use them. So we'll go back here. All right, so here's some of the things we're going to talk about. We're going to talk about assemblies, the hub battery. Does anybody know what the hub battery is? You know what it does, though? Okay, go ahead. Give me your best college try. What happens if you take it out? Okay, so that's actually not true. It has to be out for more than 30 seconds. So you have 30 seconds from the time you take that battery out for the radio to completely discharge to swap out a new hub battery, believe it or not. So you do have a little bit of time in there. One of the things you can do to alleviate that is you can keep a battery on the back and leave the radio powered on, because the radio can actually be powered with one battery. Or you can connect a power supply. So you can actively have the radio on while you're swapping the hub, and then you don't even have to worry about losing all those configurations you did. Does that make sense? So the hub battery is what's responsible. It's about 3.5 volts or 2.6 volts, I believe is what your TO actually says. And it is responsible for keeping all those configurations within your radio. So there are many radios that have these, I believe. Sergeant Boudreaux, do you guys go over any radios in Block 1 that have hub batteries in them? Okay. What about you? Oh, Sarnhoffel left, didn't he? I was going to say, because I don't know what they do in Block 6 that pertains to that. But yeah, hub batteries are used in a lot of the radios y'all are going to use in the schoolhouse. So that's their job. Okay, thank you. All right, so we're also going to talk about transmit signal flow. We're going to talk about clear voice, data, encryption. Say again? Oh yeah, what's the radio you guys use? It's the 117 Golf, right? Okay. Okay. The Dagger has a hub battery in it as well. I didn't know that. Oh, that's cool. Yeah, so those are two of the things you guys are going to learn about later. Um, we talk about the Dagger briefly in this block as well. If y'all are reading in the SciGuy workbook, it's a Defense Advanced GPS receiver. That's what it stands for. Not like Dagger, like stab stab. No, they're talking about something used to coordinate GPS for the radios and get timing. So we'll talk about transit signal flow. I'll say that again. We'll talk about clear voice, data, and encryption. And then on the receive side, we have to receive those things. Is that correct? Because if we transmit something, it has to go somewhere, yes? All right, cool. I love this interaction. It's great. I know it's early. All right, so what is clear voice? Let me ask. Let's see who we got in here. Let's ask Aaron Rodriguez. What is clear voice? Do you know what it is when it's talking about clear voice? Are you trying to look it up? All right, let's get an assist from somebody else. Looks like he maybe stepped away for a second. Aaron Mena, what about you? You know what clear voice is? I'm just gonna keep going down the list here. All right, Aaron Mena, you got this? Oh, for clear voice? What did you guys do when you went into the lab yesterday? How did you talk to each other? Yeah, I can hear you now. Sure, a clear transmission. Noise or distortion? Okay. Well, we don't want any noise or distortion when we're transmitting anyway, correct? Whether it's clear or not. So, what is clear? When we pick up a, you guys have all seen like a crystal ball in like movies and stuff before, correct? It's clear, right? What does that mean? No, no, it's if the ball is clear, what can you do? You can see through it, right? You can see through it. That's what I'm looking for there. All right, I know that was a little off the wall analogy for y'all, but it's clear, meaning there's nothing inside of it, correct? Okay, so when we talk about clear, we're talking about it not having any encryption on the line. So what the mode you guys were talking in yesterday was called PT or plain text mode, and you had two other modes on the radio. Do you guys remember what they were? I know you didn't go to them, but maybe your instructor briefly talked about them. So you had CC and CT mode. Does that ring a bell for anybody in here? Okay, so CC mode is Citadel cover mode, and that's what we use for NATO and our allies. And then we have CT mode, which is ciphertext mode. That's one we use for DoD encryption. That's our DoD Type 1 encryption for the radio. That's the NSA standard there. And that's what we use to talk to our US allies. We keep that to ourselves. We don't share that key with anybody. Some interesting things is with the CT, you can load that crypto from another device, another DSD or a Kick or a Koi 18 back in the day is what I had. It was literally a piece of paper, like tape with punch holes in it, and you had to load that and pull a piece of paper through this thing to get the crypto loaded into the machine, into another machine, and then load that machine with the into the radio, into the MPRC 150. Pretty crazy. Now they have a lot more advanced technology. They use things like a DSD, which you guys are going to learn about. I think in Block 8, right, Sergeant Boudreaux? They use the DSD? Or SKL, sorry, that's what I meant. Yeah. Yeah, they might be a little too young for that reference, but yeah, so what he's talking about is a device y'all are going to get to use later. That's a lot better than what I had when I came in. It's a Windows-based device, and that's what most crypto devices are going to use. All right, let's move on here. But does that make sense to y'all? Like the clear encrypted thing, clear versus encrypted? Cool. Okay, so we'll talk about the theory of operations next. So we're going to give you a little bit of clarifications on the difference between an assembly and a subassembly, and I'm going to kind of skip ahead here in a second and show you guys the diagram. So A2 is the designator. That's what they're talking about for the entire assembly. What they mean by that is if you're looking at your actual diagram over here, this. So they say A2, they mean this, the whole thing, right? Oh, that was a bad example right there. So this whole thing right here is A2, this whole section up here. All right, now within that section, we have smaller things called subassemblies. If you can see this, I can zoom in a little bit here. Can y'all see this? Enhance. So yeah, so if you have the hard copy sitting in front of you, that's fantastic. So if you look at this down here, this is the thing they're talking about on that slide next. It's called a subassembly or a submodule. And that means everything that's taking place inside of this submodule is only taking place in here, in these dotted outlines, just like you cut out little kindergarten sheets in paper. In kindergarten, if you guys all did that, I used to do that. I don't know how they do arts and crafts in kindergarten anymore. But you follow along these dotted lines here and you cut this out, and that's your little section. That's your little submodule right there. And that's what works for you. And we'll get into explaining this a little bit more as I get into this section for y'all. I don't want to get too far ahead of myself here. But is that clear on what's a submodule versus a module? A little bit. Is there something that's still confusing you? Okay, we're going to get there. It's going to be, I think, a lot easier for you as I explain it when we get there. But right now, I just want you to know the difference between an assembly and a subassembly, or in a module and a submodule. And those words are interchangeable, and you'll hear me interchange them quite a bit as we go through this. If you guys go to 3-1 in your intermediate maintenance manual, we have brief breakdowns of the chassis, the A1 chassis, the A2 lower chassis, the A3 upper chassis, the A4 rear panel, and the A5 KDU. So we'll start by talking about A1 right here. Y'all see this? This is the chassis. In class, I often like to call this the turtle shell because one, the radio is green, and two, what does a turtle shell do for a turtle? It protects it. It protects the guts, right? All this stuff you guys see on the inside here. We want to protect all of that stuff from getting damaged, and that's the point of a chassis in any radio. Just like your car, the chassis protects the car from getting damaged, correct? Maybe not some of these newer cars. They're made of carbon fiber and stuff. Need those old steel cars. All right. So we talked about A1 chassis. A1 protects the A2 lower chassis assembly and the A3 upper chassis assembly. It receives direct current or DC power from the A4 rear panel assembly, and it distributes the DC power to the other RT, receiver transmitter assemblies. That's what R/T is. It provides a mounting structure for the front panel interface and connectors in the A5 KDU. Does anybody know what another name for the A5 KDU is? You do not. Anybody else? No? So it's the MMI. The MMI is another name for a man-machine interface. So then we'll talk about A2 next. A2 is used for processing voice and data signals. It supervises control functions for the entire radio. It also contains the encryption and crypto assemblies. Remember we were talking about CCI yesterday? I know you guys weren't in the chat yesterday, but if you listen to the video up above, I discussed CCI. And does anybody know what CCI is? Sarmbudro, what's CCI? Yeah, cryptographic controlled item. So yep, any item that can hold ComSec. Awesome. So the radios you guys were working on are CCI radios because we have what's called a CCI module in them. This crypto assembly right here is what holds it. It's got a module in there, a little chip. The A2, A5 is what we use it for back here. So we'll go forward a little bit. So this section right here, A2, A5, that's our embedded crypto assembly. And we're going to get more into this when we talk about the transient signal flow. The A2, A5 is responsible for holding that crypto, and that's what designates the radio as a CCI radio. Even if you don't have any crypto loaded into the radio, because this is embedded, that's why we can't allow students to be in the room by themselves, because there is embedded crypto inside the radio, even if it's not loaded. That's also why these radios probably cost about $20,000 if you all saw the price tag on them the other day. You were informed. That's good. So A3 is what we talk about next. A3 contains the analog RF sections of the radio. It's the receiver, the exciter, the filters, the power amp, tuning circuits, and the analog 240 kilohertz IF. That's our first IF. We'll talk about that. Are there any questions so far? Am I going too fast for anybody? Okay. So next, the A4 rear panel assembly. This is literally the back part of the radio y'all are looking at. This is just the inside view of the back part of the radio. So these got these little tamper screws here, things like that. So it contains the radio power supply assembly, provides the interface connector to the batteries, and the hub protects the memory. So we just talked about the hub a minute ago, and you're going to keep talking about the hub because it's important. It is one of those things you have to remember to swap out. It's something you guys are going to have to do as a PMI if you actively use this radio. When I was at Fairchild Air Force Base, we constantly had to use this radio on exercises. So this radio is relevant. There are newer versions of this radio. There's a AMPRC 160 out there. We actually have a couple in the schoolhouse. Maybe I can get Sergeant Jones to come show you guys that if he's in. But they use that currently in the ECSR course. So if y'all come back through for the 5-level course, you'll get to see the newer radio. And maybe in the future, if you come back as an instructor, even we might have these radios. I don't know if anybody in here is thinking about doing that. No response. That's okay. So the A4 rear panel assembly holds the hub, the hold up battery. It's for protecting memory, like we said. And we'll talk about the J9 accessory port. The J9 accessory port is a connector for engineering development purposes only. It is not intended for use for customer application. Basically, don't touch it. You have something called the J6 accessory port on the front panel of the radio for you guys if you have to do any kind of accessory modification or anything like that for the radio. The reason we say don't touch the J9 accessory port is because you can do things called firmware updates in there. Is anybody familiar with how to hack a Nintendo DS or a Switch or anything like that? What, you don't? Okay. You're just saying that because I'm recording you. So if you are familiar with the process behind doing that, you have to go in and internally modify some things with the firmware. If you do something wrong with the firmware modification, what do you guys think happens to the device? It bricks. It turns into a big old paperweight. Yeah, you just spent $250 and then you brick something. So you can't use it anymore. It's good for a paperweight. Absolutely. So that's why we don't touch it on this radio, because I told you it costs $20,000. That's very expensive. It's a very expensive mistake right there. Yes, it is. So J10 and J11, those are the battery connectors on the back here, right here, and right here. like I said before, see how the hub is right here? And you guys were talking about replacing the hub and how it drops it. It doesn't drop it immediately. So that's part of the reason they installed another power outlet right here, is so you can swap this battery out, this hub battery right here, which is going to be a green and white battery. That's typically the only colors I've seen for a hub battery. I've never seen them be a different color, but that's what it's going to look like. Now, one of the things you do want to do is when you store this radio for long periods of time, or you're not using it for mission or things like that, or any radio really, if you're going to be storing them in what's like a cold storage, it's not actively being used. The only time you're taking it out is to, maybe blow some dust off of it because a PMI says to do that. And you're going to remove this hub battery, and you will remove any other batteries as well. Do you guys know why, or can you take a guess as to why you would want to remove a battery? Absolutely, that is definitely one of the reasons. Yep, 100%. Battery acid's not a good thing. So we had an incident at my last base where an airman took what's called a wet cell battery and tipped it on the side. Can you guys guess what happened to our carpet because he did that? Oh yeah, it ate a hole through the carpet in our building. Yeah, it literally chewed a hole through the carpet, and it could have started a fire had it came in contact with anything else electrical, really. That was the big issue. So if you ever have to do maintenance on the giant voice systems, and you have to take those batteries physically out and bring them back to your office, make sure you store them and put them upright, and do not tip them over. It's definitely something that happens. And it's kind of like one of those things you don't think about it when you're in the moment doing it, but as you go through your career and you guys learn these things, we were all airmen once. I'm sure myself, Sarmbuja, or anybody else in here, we've all made our share of mistakes, and that's why we're sharing them with you guys. It helps you guys learn. Oh yeah. Let's see. So A5, that contains the KDU. That's what we were talking about. You guys got to touch this yesterday. Did he let you take it off at all? Okay, so you guys see this interlocking. Oh, go ahead. Yeah, so that's why there is a lock tab. So the newer radio, the 160 that I was telling you guys about, it does not have this capability anymore because they found that people in the field weren't really using it and that it wasn't really working that well. So that's why they took it off. But yeah, so this 6 foot cable, there's a little thing you guys can't see on the diagram back here, but there's a little connector right here. It's called a TA3 rose connector, and it goes to the front of the MMA or MMI, the man machine interface connector right here. And then you can remote it and move it up to your arm, look like you're in an old army movie or something. But that's all it's for. But y'all got to use this yesterday, correct? You got to use the front panel and program everything. Perfect. So what mode of the radio were you in? Did he tell you guys, or do you remember what mode it is when you start the radio? Okay, you're in the manual what? That's not the mode you're in. That's a channel, what you're referring to. That's the manual channel 000. Did he tell you that typically we don't program that channel? Okay, so you guys weren't in the session I talked about yesterday, so you kind of missed that. But yeah, typically that channel, you're not going to program that channel because you want to leave it free for maintenance. Do you guys know how many channels you have available to you? 200 is correct. What about system presets? Outstanding. Very good. So open up your guys' TOs to this portion here, the 3.3.1.1. I'm going to go ahead and pull mine up too, so I'll read through this part as well. And I'll kind of give you guys a brief overview of what I know about the radio already as we go through this section. I know Sergeant Hagen's in here as well. He's here to learn this portion as well. So we have the J1, that's our audio connector. That's what you guys got to use yesterday. Did you all do the call signs? This is Mike, Victor, Hotel, Whiskey, Charlie, whatever, calling, headquarters or whatever you guys did. I think it's like Raptor headquarters. Those are the call signs y'all use, correct? Do y'all enjoy that? Yeah, good. Everybody feels pretty comfortable talking on the radio. Good. All right, so now we're going to kind of learn what was happening to that audio that y'all were using, that you were speaking, as it goes through the radio. That's the whole part of this portion right here, what we're going to learn about. Okay, so everyone's got this pulled up? Yeah, 3.3.1.1. That's the TO. So your intermediate maintenance manual too, you need to be in that one, not the operations manual, the Amperes Theory 150 operations manual. And this, as we go through this will kind of help you guys on test day as well, because you get this TO on test day. And so going through this stuff the way I'm doing it now is going to help you guys. I hope. I mean, I'm hoping what I'm doing right now is helping anybody. Is it helping y'all? Good. All right. So if y'all are on that section, you probably pulled up. We start with the J1, the audio. We're going to start with that, not the data, because we don't get to process data in class as much, so I'm not going to touch too much on that. We'll have a quick session on it after we talk about the audio. But what we do is we come in through this J1 here. I'm pointing at my screen like you guys can see me pointing. So we come in at the J1 here, the audio portion right here. What does our audio come in as? So we know that data is considered digital. What do you guys think audio is considered? AC, what do you mean? It comes in analog? It comes in analog, yes. AC, I've never heard that term used for analog. Usually that's alternating current. So yes, it does come in as analog voice, right? Good. So it comes in as analog. That's what your voice is. And it goes to this thing right here called the ALC, not the A1C, which is this thing next to it that often gets confused, is also not called the A1C. There's a chip right here called the AIC. But the first thing comes into is the ALC. The ALC is the automatic level control chip, or automatic level control, not chip. It's used for adjusting varying voice levels as they enter the radio. So as your voice comes into the radio, and you all have different patterns in how you talk. I have a different pattern in how I talk when I'm on the radio than when I'm talking to you guys in person, or even right now, as my voice comes across. This chip right here, or this controller, this analog level control, it's going to adjust those levels so that they're constant as they go through the radio, and they stay that way, so that we don't damage any of these small sensitive components. Make sense? All right, I hope you all are paying attention because I got questions at the end. All right. So then we go to the AIC next, and if you're following along your book, that's the next portion in there. It's called the Analog Interface Chip. And now I'm not talking about chips like Heinz, Lay's, things like that, not something you munch on. That's not what we're talking about here. We're talking about an actual computer chip. So this will take that analog information and it's going to digitize it. Why do you guys think it's going to digitize that information? Okay, what else? Other than just sending it, what do we know about digital technology versus analog going through things like this? Yeah, yeah, that's a great answer right there. I like that. So yeah, it's much easier to understand and translate, like he said, going through the radio than it is if it was analog. The digital communications has a much easier time coming through and being manipulated than an analog signal would. Now that's not to say we're not going to change it back to analog later, because you guys don't understand beep boop as a robot would, do you? No, you don't, because you're not robots. So you don't understand that. All right. So after we do that, it's digital now. We're going to this thing called the VDP next. It's the Enhanced by Voice Data Processor. That Voice Data Processor is what VDP stands for. So what this does is it enhances that audio coming in and kind of cleans it up a little bit. So maybe you have like a small scratchy, voice sounds like that, or you talk really high, or you talk really mousy. It kind of takes your voice and it will manipulate it so that it sounds normal. as you're talking. Does that make sense? Perfect. Kind of. It's cleaning that voice up. It wants to clean it up as it sends it through so that the rest of the circuitry we're sending it through here can manipulate it and understand it better. Say again? Oh, that like the NPR kind of voice, that guy? Okay. Yeah. It kind of just helps kind of clean that up a little bit, that's all. So that represents more of what you would naturally sound like. I mean, if you do naturally sound like a mousy or like high pitched person, it's going to represent that. You know, it's kind of like the difference between using a crappy microphone on like a PS4 and the difference between using like a really nice microphone. Have you all heard that before? Like one may sound like it's clipping a lot or in and out. Okay, cool. I know everyone's like gamers in here, so it's pretty easy to relate the stuff to that. And if I'm going too fast at any point for anybody in here, please stop me, let me know, say something in the chat. I have it pulled up. Is everything AJ squared away so far? Everybody's understanding everything? Okay, perfect. And again, I'm going to upload this video for y'all later too to go through it. So next we go to the PTF-PGA. That's the plain text field programmable gate array. That's a mouthful. All this is doing is the same thing that a traffic cop would do standing out in the road. What does a traffic cop do? He directs traffic. That's his whole job. So you guys were in clear mode yesterday, correct? Or plain text. You see how it says PT on the bottom there? Okay, so if you were to switch to any of these other modes, we're going to come back and go through this again and get into that. But if you were going to switch the radio physically, you know, take your little front panel switch, whatever, and switch to these sections up here, this is where it would go. So if you switch it to CC, it would still stay inside of this section right here, correct? Based on what I taught you guys about assemblies and sub-assemblies. So are we in an assembly or a sub-assembly right now? Correct. However, technically we're in both, right? So an assembly is the whole thing, right? The whole moving parts. So you're in a assembly and a subassembly because you're inside of the A2 assembly, but you're inside of specifically the subassembly A2 A4 right now, right? So if I were to ask you where does voice and data get cleaned up, what subassembly, what would you tell me? Not A4, A2 A4. Right? So A2 is the designator for the first numbers here, A2, that's the designator for the assembly itself. Then the second numbers are the designator for the subassembly. It's assembly A2, subassembly A4. Make sense? That's how they kind of break it down in electronics, so it makes more sense for y'all. And so it makes more sense as you're going through the circuits. Otherwise, it would get confusing, right? We wouldn't want to call this A2, A3, A4, A5, A whatever. You wouldn't want to have it too long because then you're going to get people confused on what's going on inside the radio. Now, here's my second question for you. Is that CT up there, is that part of the A2, A4? Outstanding. So remember what I told you earlier about these dotted lines, right? Y'all remember? If it's not in them, yep, go ahead. Yeah, it's going to be part of a different subassembly, right? So here's another follow-up question for you. What assembly does the ALC exist in? So think about the question. What assembly is the ALC in? No. Oh, he got it. A2. Yeah, he got it. You see what I did there? Does that make sense? See, I understand why you wanted to say A2, A4, but do you understand why it's A2? Okay, cool. Very good. All right, so let's move on. So our traffic cop, he routed our traffic. We're going through that plain text. We were in clear mode just like y'all were talking in yesterday. So this is how your traffic traveled yesterday within the internal guts of your radio. So we went through the CFPGA. It doesn't really talk about this much in your books. It's the controlled field programmable gate array. All it's going to do is, if it's data, it would have forced it to go through this modem right here, but it's not data right now, so it's not going to modulate, demodulate that data because we're not sending data. So it doesn't need to process that. It's going to go through this CDSP, which is the control data signal processor. Again, just going to pass right through it. Not really doing too much that we need to know right now. And then we go through this DIFASIC. That's the digital intermediate frequency application specific integrated circuit. No, you do not need to memorize that term. Does anybody need me to repeat that though? Okay, so it's literally right here too. So digital intermediate frequency application specific integrated circuit. That's what that stands for. But here's what I need you to know about it. It's located in your TO if you're following along right now. Is anybody following along in section 3.3.1.1? Because if you are, it's literally going in order with exactly what I'm telling you guys. Now, I'm just kind of summarizing some things and going through it a little quicker, but your TO is what you're going to have on test day, yes? So if you're following along, it's benefiting you right now. You will also have your circuits and diagrams as well. The sheet that you have in front of you, I know one of you said you had that. I think that was you, Raina. Yeah. That's fantastic. For what we're going over right now, I think it's really important that you guys have the physical copies in front of you as well. That being said, if I am going too fast and anybody wants to write notes on their circuits and diagrams, please let me know. Does anybody want to do that? Okay. Okay. All right, so let's go back and talk about this DIF, the digital intermediate frequency application specific integrated circuit. What this does is it modulates that digital analog conversion takes place there. That's the first IF. So we talk about this first IF. This is it here as well, but it's analog here. So we don't care about that yet. Right now it's generated in here, this 240 kilohertz, but it's digital. So it's not converted yet. So that's what we use the thing here for. It's going to take that signal coming in and put it down to 240 kilohertz or up to 240 kilohertz. And then it's going to digitally modulate it to produce our correct modulated waveform, because we're about to go through a whole portion of analog sections in the A3. And if it's not at the correct kilohertz or the correct frequency of what it needs to be at, then it's not going to work. It's not going to allow it to send it through the radio. It's going to mess up a whole bunch of things. So next we go to this digital IF, the digital intermediate frequency digital to analog conversion. That's what D/A is. Do y'all have see that? It says D/A and not A/D. Yes. Maybe. Okay. If you can't find it in the TO, it's also on that paper copy of the diagram you have. Okay. So whenever you see this D/A right here, that's your easy indicator that it's a digital to analog conversion. Now remember that, because when we come back through on the receive side, what do you think it's going to say? A to D. Very good. Outstanding. Look at you paying attention. All right. Yeah, it'll be analog to digital, because we're going to have to undo basically everything we just did so that you can understand it on the distant end. So the analog 240 kilohertz IF is then going to leave and go out of the A2, A1. Now, at this point, this is what's called our first IF, and it is 240 kilohertz. Does that make sense so far? Any questions on that? Any questions on A2 before we move on to A3? It's always going to be 240 kilohertz, 100%. All right. There's a reason for that, so we're going to get into that. All right. So the next section here is going to be A3. So we're going to talk about A3. Anything less than a 1 megahertz will pass unchanged to the next stage, and it gets rid of noise. That's what's happening right here. So we have this, but first there's an attenuator here, which y'all can't really see that good, so I'll go back out to the big diagram. So there's an attenuator right here. I want to talk about that real quick. Do you guys know what an attenuator does? I believe you learned about them in Block 1, Saran Boudreaux. Negative. Okay. Do you guys know what attenuation is? Do you know what gain is? So you know that gain is measured in dB when we're talking about radios, right? So what do you think an attenuator is going to do? Doesn't regulate it. It takes away from it, so it subtracts, right? So our total gain may be really high coming into the radio. Maybe you have somebody who's talking super high, or their voice is really quiet, or whatever. This attenuator is going to remove 13 dB of gain basically from that signal, so that the signal strength is not too hot coming into this next couple portions we have here, because we have a lot of filters, amps, attenuator. We got some small circuitry coming up in this next section in A3, and we don't want to blow that small circuitry. Make sense? Okay, cool. All right. Okay. So anything that's not 1 megahertz is going to pass unchanged to the next stage, and it gets rid of noise. So that's what a low pass filter does. So it has to be at least 1 megahertz or below coming into our mixer here. Do you guys know what mixers do? Yeah, you remember talking about that heterodyning thing in the beginning of the block? Right? You combine the sum, the difference, the two original frequencies, and the carrier, and you get the output. So that's what we're doing here. We're doing mixing. Now we're going to add something in here as well, this local oscillator frequency here. We're going to add local oscillator frequency 2. It's a 140.16 megahertz local oscillator frequency, and this is a 140.4 megahertz IF. That's what's coming out. So don't confuse these two. This frequency down here, this is what's known as the injection frequency. Now you may not find that specific wording in your TO. Your study guide workbooks might talk about it, but know that this coming right here, this is called the injection frequency, the 140.16. Now somebody do some quick maths for me and add 140.16 plus 240 kilohertz. So 140.16 plus 0.240. And tell me what you get. I know 140.16 plus 0.240. Outstanding. 140.4. Does that explain why it has to be 240 kilohertz for the first IF? It's so you get this exact 140.4 megahertz IF right here. This number is very important to the rest of the circuitry, and we're going to learn that in a second. And you guys are going to have a aha moment, I promise, in a second here. But everything makes sense so far? Cool. Hopefully you all aren't just saying yes sir. Okay, I was waiting for him to say yes sir to that. Okay, so that 140.4 megahertz then goes through this bandpass filter here. Again, I'm pointing at my screen with my finger like you guys can see it. So this 140.4 megahertz goes through this bandpass filter right here. That's why it had to be those specific numbers. And it has a 40 kilohertz bandwidth. So that means it can go up or down 40 kilohertz right here. So this 140.4, right? Make sense? Because there might be a little bit of fluctuation, but it's only allowing 40 kilohertz to pass through. That's it. All right. So from there, it's going to go to an amp. Now, let me ask you guys a question. You're going to have to reach back to your Dolan days. Do you remember what amps do? The signal, right? Yeah, you got it. Yeah. So why do you think we have a bunch of amps in this circuitry right here in this analog section? What do you know about filters and attenuators that I just told you? What does an attenuator do again? it lowers the signal, right? It lowers that overall gain in the signal, the strength, basically. It's lowering the strength of the signal, right? So that's kind of going to bring our signal down. All right, what about filters? Do filters do that? Do they kind of lower signal strength too? What do you think? Yeah, they clean them up, but does that also kind of distort the signal a little bit, maybe? Yeah, and then what about a mixer? What happens when you go through a mixer? You're Yeah, but you're probably going to lose some of that signal strength along that process, correct? Right, so then we have an amp, and what did you just tell me an amp does? Yeah, so you amplify that signal. So does that make sense why there's these amps here to you guys? Why these two amps are here? Yeah, you don't want the signal to get too weak because then it won't even make it through the rest of these circuits in here. Awesome. So then we go to this, yeah, right? Makes sense. So then we go through this thing called a digital attenuator next. Do you guys know what a digital attenuator does? Ooh, close, but not quite there. All right, so this diagram, real quick, this one's talking about your PLL and your voltage control oscillator here. This is how they got that local oscillator frequency. They did something called PLL, which is phase lock looping. I just want to go over that real quick for y'all. Phase lock looping takes the signal and shoots it back into here until it gets to that 140.16, which we call a what? What is this 140.16? Y'all remember what kind of frequency I called it? Injection frequency. Outstanding. Yep, 140.16 injection frequency goes into the mixer. Cool. I don't want to touch on that too much. I just want you to understand that. So then we went through here. We went through our bandpass filter like I explained to y'all. And then we got this thing here, these digital attenuators, right? So you were talking about it controlling or regulating the gain, yes? Okay, so that's kind of what it's doing. But notice it's not set to a specific number, right? Like this one over here is. It's not specifically set to 13 dB of signal strength. This one is responsible for something a little different. It's part of the TGC, or transmit gain control. Now I said TGC, not THC. That's stuff that's legal in, Washington State, right? Okay, so TGC. So it holds the power at the antenna constant while variable voice levels are coming in. Why do you think you want to hold the power constant at the antenna? Right? Because you guys are speaking, you're speaking naturally like we're talking now and trying to transmit to the other end. Why would you want to hold the antenna power constant? What do you know about the distant end? Yeah, what do you know about the distant end? Do they have a specifically frequency that's tuned for receiving? Right, so you want to hold that power constant so that specific frequency that's tuned doesn't go out of whack and not understand what you're transmitting through the signal or through the circuitry here. So also by holding that constant, your voice levels will not be fluctuating, right? They won't be going up and down or varying on the distant end. And what do we use on the distant end to listen? Yeah, for you to physically listen on the distant end, right? I talk into it too. It's the same thing you talked into. What do they have on the distant end? They have a handset, right? And you wouldn't want that voice level to be going up and down while someone's talking, would you? No, it'd be really hard to understand them, right? So that's what these are doing. They're keeping that constant. Now we got the math done down for you guys here already, but I was going to ask you all to write this out, but I figured I made you all do too much math already. So hopefully this makes sense on the bottom here, and I'll explain it to the best of my ability to y'all. So when we mix the second IF output, the 140.4 megahertz, and that variable LO1, so that's right here, this guy right here, this is LO1. I know this is LO2, which is weird when you're thinking about it. Why did they not put 1 and then 2? But it'll make sense when we come back through on the other side, I promise. So this mixer generates the carrier frequency, the 1.6 to 59.999 megahertz, which is what? 4. Not for HF. Nope, not FM. What is this the frequency range for? What were you guys programming yesterday? Yeah, it's the frequency range for the specific radio you were programming for the ANPRC 150. Now, I want to touch on that thing you said real quick. What is the HF frequency range? I mentioned it earlier. So not for the radio. What is the HF frequency range? Not millihertz. And that's not, yeah. So you said 1.6 to 29.999? Okay, now remember, I said HF frequency range, not HF frequency range for the radio. So try again. That was the HF frequency range you gave me for the radio, which is good, but that's not the HF frequency range. You can help him out. It might not even be in your book, because this is something typically in person that I would go over verbally. Did you guys, Sergeant Boudreaux, do you guys go over the 330, 3300 rule in block 1? Yeah, that's one of those things you talk about. All right, so if you guys know how this works for frequency ranges, they go from 3 to 30, 30 to 300, 300 to 3. And that's typically how it's going to go all the way up the spectrum. So the frequency range, I'll tell you guys, the frequency range for HF is 3 to 30 megahertz. Okay. So the radio is capable of doing a little bit below the HF frequency range and a little bit above the HF frequency range, meaning it can do a tiny bit of VHF so that you can use that FM. You weren't wrong with what you were saying, but the FM is used for what? I know you guys read it in your first section. In 1 alpha, it talks about FM. What is it used for? Do you remember? With this radio specifically. Oh, I hear him leafing through the book. That's okay. Yeah, if you have to look through your notes, that's understandable. And I'll give you guys a break in a couple minutes here because I know we're approaching about an hour of sitting here talking. All right, I'll give you another couple seconds and I'll just tell you. Oh, you guys are just gonna wait the clock out. All right, so it's okay. It's the FM is used in this radio specifically to talk to sister services and aircraft. That's what it's used for. Yeah, line of sight. Yes, you're gonna have to see it. Yes, right. Absolutely. Yeah, absolutely. Line of sight communication. Yep. And you'll learn more about that in your other blocks as well. Specifically, block 7, we talk about line of sight. Okay. So the next thing we're going to talk about here is we're still in A3A1, so keep that in mind. So this is the A3 section is considered the analog RF section of the radio, in case you guys didn't catch that earlier when it briefly described it. So there's no more, we're not really worrying about the digital stuff here as much. I know those say digital attenuators, but we're not really worrying about those digital manipulations of ones and zeros as much anymore. We're more worrying about manipulating RF at this point, and which it is RF at this point. So keep that in mind. So let me ask you guys a question and see if you remember based on what we've gone over so far. Where is the first IF located? A2, A1, very good, right? So that A2 section, what is the first IF? What's the number associated with it? 240 kilohertz, outstanding. What about the second IF? Yep, 140.4 megahertz. And where is that located? A3A1, outstanding. Very good. Okay, so next we're going to go through this section here. In the back of the room, in the classroom, y'all probably saw the base station configuration. Did he show that to you guys? Or did you see it, the big box, when you walk into the room? It's pretty hard to miss it. Okay. Okay, so I'll kind of tell you guys what that is and what we would use that for. So that's a power amp is what it's attached there, and it's got about 250, I think, to 300 watts is what it is, or it's a 250 watt power amplifier. You would use that for long haul HF. Like HF is typically used for long haul communications, but that thing allows you to boost your signal even further and go quite a long distance. That approximate 1,500 miles that we talked about yesterday, I talked about that, and that's also in your study guide workbook as well, is that the HF signals can travel approximately 1,500 miles. There have been some instances where I've heard people using HF at nighttime to talk to much further, and that has to do with the ionosphere thinning and being able to shoot the signal further. The problem with having too much power, though, is you can actually end up piercing through that F layer and not get your communications across, so that can be a problem as well. So we'll go through another low pass filter here. This exciter bypass path, this is only used when you have that PA, that external power amp connected. So the configuration you guys were using the other day, it did not use this. It just went straight through this section up here. That's all it did, right? Yes, the one station would use that if it was turned on. So remember that too, right? So you can still use that station in a regular configuration. You're not required to use that. Now, your command post sections on most of the bases y'all are going to, they're going to have this configuration set up. They're going to have some form of HF radio in there as a backup, or tertiary communications, which means a third communication setup to what they initially use for HF or any other kind of comms as a backup. So, and they may not always have it on, because you can communicate without it, but it allows you, it basically gives you another capability of going further with your HF signal. Something to note, and this is also in your books as well, in your TO, when you do use the external PA connected, it reduces the signal by another 23 dB. Why do you think it's doing that? What do you know about power in relation to gain, or in relation to decibels? If I increase the power, what do you think is going to happen to that decibel number? Yeah, it's going to go up. So why do you think it has to be attenuated or reduced here? Right? Because I can use the word attenuated, correct? Yeah, so you keep the same frequency range, you keep the same power going through the radio. Absolutely. Very good. Look at you, paying attention. I like it. All right. So we'll do this next little section here, and then I'll probably give you guys a quick, like, 5-minute break. Or actually, unless y'all want to take a quick break now. Y'all need, like, a quick 5-minute? Okay, I like that motivation. I like it. All right, so we'll talk about the final PA next. This is the A3, A2 section. So our final PA is the final power amplification. Now remember, see what it says specifically down here. If you have that external PA, you're not going to use this. You don't need that extra push of power because you constantly have that extra push of power coming from that power amp. It doesn't need a final push to go through all these filters. Okay? It's not worried about losing gain as it goes through here or losing dB levels. That's not something the signal is going to be worried about or the radio is going to be worried about. It's going to have that constant power amplification. So if you guys go to table 3-2 in your intermediate maintenance manual and follow along with this section here, it looks something like this. This is what it should look like. I'm going to ask you a question based on this in a second here. So everybody go ahead and get to this table. And then I'll go through this part first, and then I'll ask the question. But the signal is routed through the various filters that attenuate harmonics. The filters are determined by frequency or modulation using table 3-2. That's where we just went in the intermediate maintenance manual. So in your manuals, you might have to look this up, but so for example, if I were to ask you if I was to use a frequency of 22 megahertz, what band would I be using? What filter band? I said 22. Yeah, 6. Band 6, absolutely. Very good. Now note that it always uses one of these bands right here. So it's either going to use BCI or HF1. If you're not in the HF1 band, If you're not in this, the 1.6 to 2.399, it's not going to use that. It's going to go through the bottom through the BCI here. Okay. Now this BCI here is also used for something very specific. The BCI is used for AME mode, which is what's used to talk to other AM radios, commercial band radios, because we have that capability in our single sideband radio. Remember, we're using a single sideband radio, so we don't naturally have that carrier that's being produced in AM radios like you guys learned about in the beginning of the block. You remember reading about those differences? We were talking about differences between single sideband and AM. Okay. Do you know any of those differences? It uses a lot less power. That's definitely an advantage. Okay. Yep, that's one of them. And we'll talk about that tomorrow. I'm going to do a review with you guys tomorrow about the same time. And we're going to comprehensively kind of go over every single one of these things for y'all, if that helps. If y'all want to do that. You said yes, you'd like to do that? Okay, great. No, this is for you guys. So I mean, this is, I'm trying to help you guys out. All right, so BCI, like you were saying, that's that AME mode. AME mode, like I was saying, is used for talking to AM radios. The reason we can use those talk to AM radios is because it actually puts a little bit more of the carrier into the signal itself. So we can normally with single sideband radios we suppress that carrier. We don't want to use it because it takes up power inside of our radio, right? Because in an AM radio, that takes up 2/3 of your power just to transmit that whole carrier all the time, and we don't do that with a single sideband radio. So right now we're introducing a tiny little bit of that back in so we can talk to those citizen band, those commercial band radios, those things that like truckers and stuff use, or hikers. If they're out in the wilderness, they can use that. My last base at Fairchild, they had a aerobatic medical squadron there, and also part of our like SEER guys. There was a lot of people that were hiking out in the woods and stuff, and they would bring radios out with them. And this is one of the capabilities that they would be able to use. They could use HF radio and talk to these guys if they were stuck out in the wilderness and go find out where they are and locate them and rescue them. So it was kind of a nice feature if you think about it. And that's a practical application for that feature. All right. Well, I mean, yeah, sure, that's a good application for it too. Yeah, that's a much more military application for it. Yeah, I like that. All right. Any questions on any of this stuff so far before we finish up here? Okay, cool. So we'll do next. We're going to talk about the high level limiter. It just kind of passes through that. Literally, the high level limiter is one of those things where like you're defining a word in a dictionary and it just does exactly what it says it does. It limits high levels. It limits those high gain from coming through and stops that. All right. That's all it's doing. So you've reached your level cap of 99. You can't go any further. All right. Yeah, there you go. He's like, that's true. Yeah, nerd stuff. All right. So we'll talk about impedance matching next. That's the antenna coupler. But before we get to that, I want to talk about this directional coupler down here. So that's the VISWAR data. That's voltage standing wave ratio data. You guys use a digital or analog power meter, Boudreaux, in block 1. Did you use a digital or an analog power meter in block 1? I think it's digital, the one y'all have, right? Do you drop the elements into it? Yeah, that's it. Yeah, the analog one. Okay, so you guys just have the RF, the digital one, right? Yeah. So what that's doing is that's measuring VISWAR for you guys. That's what it does. It's the voltage standing wave ratio. So you don't want a ratio that's too high because that will cause problems in your signal and cause what's called reflected waves to come back into the radio. Now, what do you guys see that's behind this section right here, behind this directional coupler section that might be a little sensitive if we were to send some waves back through it? What are these things that I have highlighted? Those are the filters. What might happen to a filter if you send a wave back through it? Yeah, you might break them. They might pop. You might see some magic smoke is what we refer to it as in maintenance or in RF and communications in general. That's like the blue smoke you talk about all the time, or it's like an electronics burning smell. Usually means you broke something or your visual is probably too high. And that can be a problem and the way you could counteract that is by putting something in line with your signal in between the antenna, right? So in between the sections right here, right before we come out of the radio, in between the antenna and the antenna coupler and the antenna is where you would put the power meter, the RF meter that Sarmbudra mentioned, is where you would put it. Okay. And that would help you measure that ratio to see if that's truly your problem, if you're getting reflected waves coming back into your radio. Newer radios, especially this radio, the 150, will pop up if there's an error, or it will tell you if there's a voltage wave ratio error. It'll actually just shut the radio down, so you don't even have to worry about measuring that reflected wave power. Some of the older radios, though, they will not do that, and you will have to actually do that yourselves. So just remember that as a troubleshooting step. It is something you might have to do in the future. Okay, so let's get back to talking about this directional coupler, right? So why do we need that VisWAR tuning data? What do you guys think? What does it say down here? Okay. Yeah, it tunes the antenna coupler and it provides the information to the TGC circuits. What were the TGC circuits again? I know, I'm asking you to remember what we talked about like 15 minutes ago. Ooh, we'll go back and talk about TGC again. I guess I could do that. Remember that stuff I said that's legal in Washington? That TGC? Yeah. All right. So it's assisting with this right here. The part of transmit gain control that holds the power at the antenna constant while variable voice levels are coming in. That's what it's helping with. Does that make sense? Okay. So it also sends bias control signals to the final amplifier. That's what this little line is down here, so that you don't overdrive this final power amp. That's what it's doing. You don't want to overdrive it. And then we talk about this antenna coupler thing next. Now, the reason the antenna coupler is so important is because it's what helps fake the electrical length, which you guys are going to learn about in block 4. You're going to learn about electrical length and measuring out wires and things like that. When I got to go TDY, I got to actually run a cable out for an antenna to talk to another state from the place we were at. And we got to actually run a 100-foot cable out of copper wire, basically, and then walk it back. And that was our antenna, because we didn't have the ability to have this antenna coupler in there. We didn't have the ability to fake that electrical length, so we had to physically run the whole wire out. This antenna coupler allows you to do that. It allows you to act as if the antenna was longer than it is. Does that make sense? Okay. It's also responsible for impedance matching, which is the coupler control tune data is used to switch the various inductor and capacitor elements into and out of the circuit until a good impedance match is found. So what is impedance matching? What is impedance? Yes, that's correct. Yep. So that's why the directional coupler does that. So it does that by using the various inductors and capacitors. That's how it does that. Right. So impedance matching is important. It's our resistance. The $10 word for impedance is resistance. Okay. I haven't heard that one before. I like that, though. So the antenna coupler, it's the impedance matching that takes place between the radio and the antenna. It's fed to today's antenna connector, and it compensates by switching capacitors and inductors. That's what it does. So you guys can actually see that breakdown right here. You see these inductors right here, and then the capacitors. Now, it's not important to really know the specific amount, the number. I don't care about that, but it's good to know that that's what's actually happening inside of here. And then we go out to the antenna connector, right? Because our radio doesn't work unless you have what connected to it. Did anybody forget the cable yesterday? You don't have to call yourself out. Somebody forgot it. Yeah, it happens. It's a very common mistake. But what happens when that occurs? Yeah, you can't receive or transmit a signal, and you're RFing yourself, right? Because that RF has nowhere to go except into you. Yeah. Oh, yeah. Oh. There you go. So it's a very common mistake, and even some of us who have been doing this for a very long time, we still forget that. Okay, just remember it. I'm sure if you made that mistake, you won't forget it again. All right, so let's antenna connector, right? So we have to connect the OE505, which is also known as the what? It says it right there. Yeah, the OE505 is also known as the what was the question? The whip antenna. All right, so that or any number of other antennas can be chosen to meet your mission requirements. In block 10, y'all are going to get to use something called a BNW, and that's going to be your HF antenna. That's the Barker and Williamson antenna. It's directional, so it's pretty cool. You guys get to set that up. You'll also get to set it up, I believe, in block 4 as well, but I don't teach block 4, so I can't speak to that. All right, I have some questions for y'all, but I think we're just gonna give y'all a quick 5-minute break here. Give y'all a chance to get up, stretch, go to the bathroom, whatever you need to do, and then come back. All right. So go ahead and do that. I'll go ahead and pause the stream here. Whew, we've been going for about an hour and 11 minutes so far. You guys are troopers. That was good. We're almost done. So the next section, it goes a lot quicker because you guys kind of understand at this point how everything's flowing, correct? So guess what? We're going to go through receive in a bit here. We still got a little bit more to do with transmit. But on the receive side, do you guys think a lot of these components and circuitry is going to change its job? Let me just ask you that. Yeah, that's absolutely correct. And that's why the second portion here is going to go a little bit quicker. Yeah, that's awesome. Yeah, that's awesome. All right. So all this is a quick summary of everything we talked about. So A1 to A4, A2, A4 does the analog to digitized audio. A201 is that digital modulation, that D/A conversion, which stands for what? Yep, digital analog. And then we have A through A1, IF to the final RF, that's the KDU frequencies. That's that frequency we're actually going to transmit, that 1.6 to 59.999 megahertz, which is the frequency range for what? Yeah, the 150C. Yeah, the RT1694 Delta. Yeah, the radio. Right? Always make sure when you guys get your radios, when you buy them in the future, go through your packing list is what it's called. We talk about it in 1 Bravo. It talks about the typical configurations or items that come with the radio. Make sure that the RT1694 is in there, because if you don't have that, you don't have the radio, and you just have a box full of accessories. Pretty not great. That actually, you would think that stuff doesn't happen, but that actually happened to us. If we ordered, yeah, we ordered a bunch of LMRs, and a couple of them just were missing accessories or missing things, or even LMR was missing out of one of the boxes. So it happens. Definitely make sure you check and call the manufacturer if you have problems when you purchase radios, because you guys may be involved with stuff like that in your future, even as airmen. All right, so the final PA, yeah, we talked about that. That's the final power amplifier, final push. When do we not use that final PA? Absolutely. How many dB does the final power amp drop, or the external power amp drop it down by? How much dB does the external power amp drop your signal down by? 23. Yeah, you guys are great. All right, and then we have something called post-selector filtering. I didn't tell you that as we were going through it, but what does post mean, right? After, right? Absolutely. And then we have the visor data. We talked about that. A3 to A5, or A3, A5 to A1, that's just your impedance matching. And then we come out the antenna. So when we talk about data, we'll briefly talk about this. It goes along the same path. Does data come in as analog is my big question. Right, so then we don't need all of these things up here, correct? We don't need this little section up here for digital. Yeah, because it's already digital. We're not going to clean it up and convert it to digital and process it because it's already there. So it's just going to go through something called a DTE, which is your data terminal equipment. That's where you're hooking it up on the back typically. That's where the radio knows that this is specifically a piece of data equipment coming through here. One of the examples I can think of is a program that you guys are going to possibly use in your future called RPA. That's a radio programming application, or CPA is what it's more commonly known as now. That's still, it's a computer programming application or communications programming application. That's what they're going to use. CPS is another program. That's the one I believe they use in Block 5, Sarm Boudreaux. Is it CPS or CPA, the one you guys use in Block 5? I think it's CPS. For the XTSs, I think it's CPS, and then I think for the newer ones, the APXs, I think it's CPA. But yeah, they're programming applications for the radios that make it easier so you guys don't have to sit there and hand jam the radio, which is definitely what you all did. And that took you all some time, correct? Yeah. Yeah, that's exactly where you'll connect it, is that J3 data port, and you'll program lots of radios very quickly. Block 5, I think they call it flashing the radio. I think that's what it's called. Maybe. Yeah. But that's something you guys are going to learn about more in Block 5, and maybe you'll have Sarm Boudreaux for that. So we'll go ahead and we'll go over that. The DTE, we talked about that. Data terminal equipment, that's where it connects. And then again, we go through PTF PGA, which does what? What does the PTF PGA do? Oh, okay. I thought you guys knew right off the bat. I got way too excited. You can't hear it in my voice, but I'm getting excited. It could be like the 3 cups of coffee I drank, though. Probably. All right, I'll tell you. It's the plain text field programmable gate array. We called it the what? No, the traffic cop, remember? Yeah, we called the PTF PGA the traffic cop. And what was the traffic cop's job? He directs traffic. All right, then we go through CFPGA. Now CFPGA is going to route this up to the modem, the modulator, demodulator, because it is data. So that's all that's going to do. It's modulating that data traffic, putting it zeros and ones, getting it where it needs to be so it can send it out, and then demodulate it later on the distant end when we receive it. Because if you modulate something on the transmit side, what do you think you do on the receive side? You demodulate. Is anybody having an aha moment right now because they didn't know modem stood for modulator, demodulator? Nice. All of it. That's good. I'm glad this is helping you guys. That's the whole purpose of doing this. All right, so then we go through the CDSP next, which is the control data signal processor. And then we stop there because what is anything different at this point? No, it's going to do all the exact same things for data. So we don't even need to go over all this stuff again. It's literally going to do everything we just talked about. Great. So then we'll talk about transmit clear voice signal flow in CC/CT. So this is actually going to be encryption we're talking about next. If you're following along in your text, it's these sections right here, 3.2.2.2, 3.3.2.4, and then 3.3.1.6, and 3.3.2.4. So now it kind of looks like it's doing both at the same time, because it is, and I wish they did this diagram a little bit differently for y'all, because this is way too confusing to just throw all these arrows in here at once. But let's say it's analog, it's audio, right? It's going to go in here. We'll start with that. It comes in, does its ALC, which does what again? Absolutely. What does that do? Yeah, it changes the varying voice level to high or to low, right? And then what about the AIC? We got the AIC next. What does that do? What does it say underneath right here? Yeah, so you didn't even have to think about it, right? And remember on test day, what do you get on test day? You get this too. You also get this diagram. So if it says stuff like that on there, make sure you guys are using the materials provided, right? You didn't even have to think about that. The answer is there for you, right? It digitizes the audio. That's what it says right here underneath. Okay, great. Then we go to the VDP. What does the VDP do? Okay, what do you mean it processes it? What does it do to the audio? What's that E word? Starts with E, ends with enhance. Enhances it. Yeah, very good. All right, great. We are going to talk about encryption though now. So now we're going to the PFTPGA again, the plain text field programmable gate array again, the traffic cop. And he says, no, we're not doing PT now. He's telling them to go to either CC or CT, which is going to do what? That other E word you just used. Encryption. And what do we do with the CT encryption? What do I tell you guys is the difference between CT and CC? Do you remember? They both hold it. They both hold encryption. But what does CT encryption? Who do we share CT encryption with? Do we share CT encryption? Only with us, right? It's only with us. All right. Is the A2A5 part of the A2A4? No. So if we're doing CT encryption, where is it going? Only to US. Only the US, not allies. All right. If we're doing CC encryption, where is it going? Allies, NATO and allies. Very good. Right. We're going to share our CC key. We're not going to give them away our CT key. That's only for us. Okay. In relation to the diagram, though, the CT goes to the A2A5 if we have CT or ciphertext, and then they both come through this ciphertext field programmable gate array. That's what CT-FPGA is. So anytime you see FPGA, think field programmable gate array, and then whatever they slap in before it is what it's going to do. Make sense so far? Okay. This part I'll explain briefly, but it can get confusing, especially when you get to a base and they tell you that red is black and black is red. But this is referring to encryption. I've been to several units where they'll flip this around on you and you're like, that's not what I learned, but just roll with it when you guys get there. So after you come through the CT-FPGA, they're going to do what's called black side encryption. So it's now encrypted at this point. We've encrypted it from our CT-FPGA. It's gone through our crypto assembly. It's gone through sit-all cover. So what do you guys think red side's going to be if black is encrypted? Yeah, red is going to be your unencrypted. Yep. Very good. And it should also say that in your book as well, if anybody's following along there. So then we go through the BIOP, the black input output processor. That's what that's called. That's also going to be responsible for controlling some of the system status functions as well, such as the KDU. So that happens in the BIOP. Then we go through the CT data because it's ciphertext, so it has to go through the modem. Ciphertext does, or CC. It's required. It has to. It has no choice. And then it does what? Yeah, it's modulated or demodulated, and then it goes back exactly the way it came in. Nothing changes. It's going to go back out exactly how it came in. Make sense? Any questions so far? We're almost through this all. Y'all are doing great. Where else can it run through, though, remember? So if it's CC, it's going to run through ATUA4, correct? If it's what? C2. Or CT. If it's CT, it's going to run through A2A5. So encryption can run through either. You have to pay attention to what a question's asking you, right? So if I were to ask you what submodule does CT happen in or ciphertext happen in? Yeah, does this help? Enhance. Yeah, there you go. So does this help? Can you see it now? All right. So it'll go through that CT if it's ciphertext, and then it goes through what subassembly? A2A5. It's like I'm giving you the answer. And then if it's CC, it goes through what? A2A4. Does that make sense? Remember, go back to that kindergarten thing I was telling you where you cut out around the dotted lines, right? It's not in there. This is not in this. Remember that. It still has to go back into the subassembly. Very good, because it still has to go back in and process through that. You're correct. Yep, black is going to be encrypted for this radio. I don't know what they talk about with other radios, or when you get to your unit, it could be completely different. They could talk about it differently, but black is encrypted for our purposes. All right, almost done here. So now we're going to talk about receiving, because we talked about transmitting already. Like you guys said, first question I'm going to ask you is obviously the one that's at the top of the screen. What do you see on here that's different? And I'll zoom in so you can all see a little better. Oh, outstanding. That's the first difference. We're starting at the antenna. What else? This is like, where's Waldo? Right, we're going backwards, so everything's reversed. Okay, what else is different? There's a couple other small things that you have to look real closely. I just highlighted it for you all, one of them. So that is what's called a notch filter. What a notch filter is going to do is it's going to improve the weak signal performance and boost it back up so that we have that 140 megahertz coming back through. So that's one of the major differences. Right, because we need that 140, as you all know, coming back through, right? Absolutely. Yep, instead of an amp, there's a low pass filter there. Okay. We had a low pass filter on the previous diagram as well, though. I think you mean this, the active band pass filter. Is that what you're talking about? Oh, it goes straight into the attenuator before going into a digital attenuator. Yeah, okay. All right, you're not wrong. All right, cool. That's the big major differences right there. So, and it literally says right here, here's our other stuff. So the top and bottom modules are swapped. You nailed that. The handset and the antenna are swapped. You got that. Each module's components are reversed, and it has a notch filter, which I explained to you. So we're going to go back through here. It's going to be pretty quick, this next section, because you all already know, for the most part, what all of this stuff is doing. The antenna coupler isn't going to change its job. Still going to do that VISWAR. Okay, still going to do that voltage standing wave ratio check. We have the directional coupler, which is going to do what? Yeah, a directional coupler. Yeah, excuse me. The directional coupler is the one that's going to do the VISWAR. The antenna coupler is going to do the what? The impedance matching, correct? I had that reversed there. Somebody should have corrected me. Y'all were listening. Very good. All right, so the impedance matching. What is impedance again? Yeah, your resistance. So your total resistance matching. So we match that resistance so we don't get that VISWAR like y'all were talking about. And that VISWAR is the voltage standing wave ratio. We don't want that reflecting back into the radio. So the signal is then routed to the notch filter. Oh, after it goes through these. RF filters right here, which we call the pre-selector network. And why do you guys think it's called the pre-selector network? It happens before selection, right? Yeah, exactly. So signals then route to a notch filter, improving weak signal performance. Like I said, we want this 140. So this is acting like an amp, but it is not an amp, right? Because this is where the final PA was located in the previous section in the transmit side. So it's acting like that, but it is not an amp. All right, after we go through there, we go through our low pass filter, our digital attenuators, which now do something called AGC instead of TGC. What was TGC again? Remind me. Okay, what was its job? What did it do? Not so much the correct frequency range as what was that varying thing coming in and out? The thing I'm doing right now. Sometimes I do it high, sometimes I do it low. What's this word up here? Yeah, it keeps the varying voice levels constant for the receiver. So that's exactly what your AGC is going to do here, right? So with TGC, it kept the varying voice levels constant for the antenna, right? Because you transmit out the antenna. Yes. So the AGC is going to do the same thing, except it's going to keep those varying voice levels constant for what? What do you listen on? On the handset. So it's going to keep it constant for the handset. So when you hear that person's voice coming back through to your side of the radio and you receive that signal, it's not going to be all over the place, and it's not going to sound like that, be all squeaky. Make sense? Awesome. So then a couple small differences we want to talk about here in the A3, A1 section. The first mixer, the LO1, produces the first IF of 140.4 megahertz. What was the first IF on transmit? 240 kilohertz. So remember, the first IF and receive is not the same. It is 140.4. Why do you think it's 140.4 for the first IF? Yeah, it's going to extract that signal back out, that frequency that we have. So right now we have the carrier frequency coming in, right? We have whatever frequency we tuned into the radio. Yes? So like if I told it to be 3 megahertz, it's at 3 megahertz, right? If I told it to be 7, it's at 7. Yes? Okay, so we have to extract that back out and put it back to what it was to get it down to this 240 kilohertz over here, which is now going to be our second IF once we get through all this. And hopefully that makes sense to you all. So it's going to do that. It's going to do its job here. It's then going to amplify and filter before being attenuated by a digital attenuator. This is part of the AGC, like I said. Going through this next portion here, we're going to mix with the 140.16 megahertz LO2, which is still our what? What was that 140.16 again called? No, not your first IF. Not the 140.16. What's that called? Do you remember? Injection frequency. Yeah, I know we've been sitting in here for almost like 2 hours and you guys are probably losing it, but that's okay. It's the injection frequency, right? So we got to put that injection frequency back in. We got to use that voltage controlled oscillator to generate that frequency, and then use the PLL, the phase lock looping, to lock that frequency in, and then shoot it back into the mixer. Because what we're going to do now is we're going to take this 140.4 and we're going to subtract it from the 140.16. Whereas on the transmit side, we did what? We added this in, right? The first IF here. But now we're subtracting it back out. So things are slightly different, but job functions are mostly the same if you have not noticed. Active bandpass filter going to do the same thing, except all it's going to do in this instance is it's going to allow this 240 through, and that's it. If this tries to fluctuate or do anything else, it won't let it through. That's it. So what is our second IF? 240, outstanding. Very good. Great. You guys are crushing it. We're almost done here. Thanks for bearing with me. I appreciate it. No problem. That's my job. So we're going to come back down here. See this digital A/D now? It's the digital analog to digital conversion instead of digital to analog conversion in the IF. So that's different. The DIF ASIC is going to keep the same job. It's going to keep that. Instead, it's going to take that analog that was digital originally and put it back to digital, or keep it at digital. So it's just going to modulate that 240 kilohertz, the IF. It's going to extract it back out, send it through. If it's plain text, it'll just go through the bottom here. If it is data, it'll go through our modem, or ciphertext or CC, it'll have to go through the modem. If not, it'll just come through the bottom. Let's see. Moving on here. Am I moving too fast for you? Okay. So the signal enters the A/D converter before being modulated at the DIFSC. The output would be intelligence. And the intelligence is what? What do you guys know about intelligence? Okay, and what kind of information is that? What is the information that we can see? Our voice, or its voice, or what? Voice or data. Very good. It's like you guys had some help there. Yeah, so it's going to be voice or data. That's what the intelligence is. So the signal is then converted to the analog audio signal. It is finally sent to the J1 audio connector. So you can do what? So you can receive it. So you can hear it, just like what y'all were doing the other day. So did this help you guys? Okay. All right. So while we're in this section here, I want to go over some real quick differences before we wrap up. So what do you guys notice is missing from here, from this section right here, that we had on transmit? Yeah, the audio level control. Yeah, audio level control. Why do you not have the audio level control? What can you do with your fingers to adjust something if it's low or high? Yeah, you can turn the volume up or down on the front of the radio. So you don't need something to do that for you. Make sense? Yeah, that's why it's not there. Okay. Data, if it's data, it'll just come through here. We'll go through that. And then ciphertext, it's going to get converted into something called red data now at this point. And the red data is going to be the unencrypted. Now, it won't be considered red data or red until after it goes through either here, this portion, the embedded crypto assembly, or it goes through here after the Citadel cover portion, right? Because it's still encrypted until it goes through one of these two devices that encrypted it originally, correct? All right, what is the process of unencrypting something called? Decryption. Outstanding. All right. Y'all did great, by the way. This was really good. Yes, it'll receive red because that's going to be unencrypted is what it's considered. Yes, for this purposes only. Now, Sergeant Boudreaux, have you heard that differently at any other bases you've been to? Yeah, I know most of the bases I've been to too. You guys gotta pay attention when you go to your command posts or when you go talk to your ComSec office. They'll tell you something different typically. They're gonna tell you red is encrypted, and you're gonna be like, well, that is definitely not what I learned, but okay. Yeah, you're just gonna have to deal with it. Yeah, just go with what they tell you. That'll help keep you out of jail. That'll be good. Definitely listen to your ComSec office. Definitely don't want to see any of you getting reported in Air Force Times for, doing something silly. All right. Does anybody have any questions? All right. Anybody in chat who wasn't talking this at all? Do you guys have any questions? Airman Lassell, Mena, Mitchell. If you guys have questions, go ahead and type them out. If not, I'm going to close the session out here. I appreciate you all listening. If you have any questions as the rest of the block goes on, please let me know. I am on Discord until about 6 o'clock every night. I'm available for questions even after hours. If you guys have any questions as you go into your other blocks, absolutely hit me up. I can try and get you in contact with the right person. All right, well, there's no further questions at this time. You guys are free to go. I appreciate it. Thanks for listening. Enjoy your lunch. Hopefully that helped you all. All right, have a good one.